Welcome. In this video, we're going to continue our study of optics. The topics I want to cover in this video are the prism, dispersion, and total reflection. Let's begin. We want to start by considering the refraction of light through a prism. Now, at first, this may not seem like the most relevant topic. You may think, well, how often do we work with prisms? Well, what I'm going to show you, the prism is very important for understanding how lenses work. And so it's very important to see exactly how light passes through a prism. So you want to follow this one closely because we're going to come back to it when we study lenses. So here we have a triangular prism made of glass. It could be plastic or glass, either one. Let's say it's glass, surrounded by air. Let's imagine a ray of light coming from the left. There's the ray of light. We want to know what's going to happen or how it's going to refract as it passes through the prism. Well, remember, we learned the law of refraction, Snell's law, and so on and so forth. But the key feature was when light crosses the boundary, if it slows down, the ray bends toward the normal. If it speeds up, it moves away from the normal. So the first thing we want to do is figure out where the normal is on this prism. Now watch closely, because the previous pictures, the boundary is typically horizontal, the normals are vertical, they're easy to see. But here is what the normal to the prism looks like. Normal is always perpendicular to the boundary. So if you want to turn your head to the side, look at that, convince yourself that dashed line, the normal, is indeed perpendicular to the boundary between the air and the glass. Now we know what's going to happen. When the ray crosses the boundary, it's going to bend toward the normal. So in this case, bending toward the normal means the ray is going to bend downward. Now it comes to the other side of the prism. Now what's going to happen? Now the ray of light is going to pass from glass to air. Just to remind you, the velocity of light in air is 3 times 10 to the 8th meters per second, essentially the same as it is in vacuum, very, very close. Glass is a much denser medium than air. The ray of light slowed down. From air to glass, it slowed down, so it bent toward the normal. But now, as it makes it to the other side of the prism, it's going to cross from glass to air. It's going to speed up. Once again, let's draw the normal. Again, turn your head to the side. Look at that dashed line. That line is perpendicular to the side of the prism. You want to have a good feeling for how to draw the normal. See the one on the left, perpendicular to the left side, one on the right, perpendicular to the right side. Now when the ray of light crosses the boundary from glass to air, it's speeding up, which means it moves away from the normal. So it bends down again. This is what's so interesting about how the prism works. Because of the angle of the two sides, when it enters on the left, for this one it bends down. When it exits on the right, once again it bends down. Now imagine if I flip this prism upside down and send the ray to it from the left, it would bend upward. So understanding that path bends down for this prism, if we flipped it upside down, it would bend upward. It's going to be very important when we come to lenses and how light is refracted through lenses. Now, for this particular problem, if you wanted to solve it quantitatively, Snell's law, n1 sine theta 1 equals n2 sine theta 2, it's rather difficult for the prism because there are so many angles involved. So we're not going to worry about that feature. We'll have another way of dealing with this refraction quantitatively when we come to lenses. For now, we want to understand qualitatively how the light refracts through the prism. Now, the next topic is called dispersion. What is dispersion? Dispersion is when refraction depends on wavelength, meaning when the light enters the glass, the speed of light in the glass depends upon the wavelength of the light. Why? Remember, as wavelength changes, the frequency changes. The frequency of the light has a large impact on how it interacts with the atoms, the molecules that make up the material. So the wavelength, typically we don't talk about the frequency of visible light, but wavelength and frequency, they track one another. They determine how the light interacts with the material. And so we find out the speed of light. The refractive index is likewise depends upon the wavelength. So here's a picture of light entering a prism. Now it says incident white light, looks like a blue arrow. Okay, you have to use your imagination a little bit with this particular picture. But the point is, the red light, which has the longer wavelength, 760 nanometers, goes faster through the glass than the violet light of 380 nanometers. Because the red light is faster, it has a smaller refractive index, bends less when it enters the prism. The violet, with a shorter wavelength, goes more slowly than the red, means that it has a larger refractive index. It bends more when it enters the prism. The result is when the light exits the prism, you see a spectrum of colors from red to violet. In fact, Isaac Newton studied the prism. He wrote a book about optics, and he introduced the word spectrum into the English language to refer to the colors separated by the prism. Okay, now a different topic. Now we want to consider the limit of refraction when n1 is greater than n2. Think about it, what it means. If n1 is greater, that means in that first medium, n1, where the light is coming from, it's going more slowly. Remember, it's c over v. V gets smaller, n gets bigger. So in the first medium, the larger refractive index, the smaller velocity. The second medium, the smaller refractive index, the larger velocity. So we see the ray of light coming from the lower left, makes it to the boundary. There's the dashed line for the normal, and it bends away from the normal. That's the refracted ray. Also, some of the light may be reflected at the boundary. Let's consider that the top medium could be air. N2 equals 1. Lower medium, the blue, could be water. N1 equals 1.33. So the ray of light goes from water to air. It bends away from the normal, and another ray is reflected. But what if the angles were such, the refractive indices were such, that the ray tried to bend so far that it went back down into the water? Because remember, theta 2 has to be greater than theta 1. If theta 1 reaches a certain critical value, then theta 2 might try to dip all the way back down into the water. It means theta 2 would be 90 degrees. If theta 2 dipped into the water, there could be no refraction. Why? Refraction depends upon the fact that the velocity of light in one medium is different from the velocity of light in another medium. If the light never crossed the boundary, there could be no refraction. So what would happen when that theta 2 approached 90 degrees and the ray dipped back into the water, right? Theta 2 has to be less than 90. If theta 2 reaches 90 and the ray dips into the water, the refraction will disappear entirely. No light leaves the first medium. It's all reflected back into the lower medium, or the starting medium. This condition is called total reflection. Total reflection. Without refraction, all of the light must be reflected, and we have total reflection. Now here's a curious thing to consider, a little bit off the topic. But you could ask the question, if all the light is reflected, how does it know? How does it aware the fact that it would have a larger velocity in the other medium? Does that incident ray sample the second medium to determine there's no refraction? That's an interesting question. In fact, if any of you ever use a technique called attenuated total reflectance, it's a technique in infrared spectroscopy. That technique is based on the fact that the incident ray very slightly samples that second medium before it's reflected. Okay, that's another topic, but you may come across that if you use infrared spectroscopy in a particular technique called ATR, attenuated total reflectance. That's not part of this course. I'm just mentioning it in case you see it. All right, let's get back to this course and consider that angle of refraction theta 2 approaching 90 degrees. It will happen when theta 1 reaches some critical angle. When theta 1 reaches that critical angle, theta 2 dips into the water. There's no refraction. If theta 1 is greater than that critical angle, well, then even more so, there's no refraction. So for theta 1 greater than or equal to the critical angle, there's total reflection. Let's look at the mathematics behind that. Okay, here's Snell's law for the two media. We want to solve for theta 2. We rearrange the equation. Sine theta 2 is n1 over n2 times sine theta 1. Let's suppose, now it's not the same as the previous. These are different numbers. Not everything happens with air. So here we have a light ray going from glass, n1 equals 1.5, into water, N2 equals 1.33. So theta 2, if you do that ratio, N1 over N2, it's 1.5 or 1.33 is 1.13. So theta 2, if you look at those equations, will be sine inverse of 1.13 sine theta 1. This is not an equation that you can use in every situation. This is specifically for glass to water. N1, 1.5 divided by N2, 1.33, gives you the 1.13. So let's consider some numbers. Okay, use this as my whiteboard. Theta 1 equal to 40 degrees. What would the what would the theta 2 angle be? If we calculate that 1.13 times sine theta 1, we find it's 0.726. So theta 2 is sine inverse of that number. Theta 2 would be 46.6 degrees. So you can go ahead and calculate this particular quantity, or just follow along with your calculator and see you'll get the same number. Now let's imagine we increase theta 1 to 60 degrees. Now we calculate that quantity, 1.13 sine theta 1. It's now equal to 0.979. Theta 2, the sine inverse of that number, 78.1 degrees. See, theta 2 will always be greater than theta 1 because the light is speeding up. Remember, it starts in the first medium, it's slower. Second medium is faster. So theta 2 is getting larger. Now let's suppose theta 1 was 80 degrees. If theta 1 is 80 degrees, that quantity, 1.13 sine theta 1 equals 1.11. Theta 2 is the sine inverse of that. Try it with your calculator. You'll find you get an error. You cannot have an angle that gives you a sine greater than 1. Therefore, if you try to do sine inverse of a number greater than 1, you'll get an error. Which means that somewhere between 60 degrees and 80 degrees, theta 1 hit the critical angle. Let's find the value of the critical angle, the point where total reflection begins. And any angle greater than the critical angle will continue to have total reflection of light. Okay, so where does this phenomenon begin? When theta 1, the angle of incidence, equals theta c, that's the critical angle. At that point, the angle of refraction, theta 2, where the light should cross the boundary, equals 90 degrees. That means the light does not cross the boundary. Stuck at the boundary, therefore, no refraction, total reflection. Snell's law. N1 sine theta 1 equals N2 sine theta 2. If theta 2 is 90 degrees, then sine theta 2 equals 1. Therefore, at this point, theta 1 is the critical angle, theta 2 is 90, sine of 90 is 1, N1 sine theta c equals N2. Rearrange the equation to solve for the critical angle. Divide by N1, take the sine inverse, theta c equals sine inverse N2 over N1. Here's the case we've been looking at. Light ray from glass, N1 equals 1.5. That's where it's slower. To water, N2 equals 1.33. That's where it's faster. Critical angle, theta C, sine inverse of 1.33 over 1.50 equals 62.5 degrees. Recall in the previous examples where we worked out, I said that the critical angle was somewhere between 60 and 80 degrees. Here we see 62.5 degrees. This is a fiber optic cable. This is a extremely, popular way to transmit massive amounts of data using a glass fiber called a fiber optic cable. You have digitized data, pulses of light. You feed them into the glass fiber. You see this thing here, it looks like a tube. This would be a extremely small glass fiber, diameter of this thing, a millimeter or less. You feed the glass, the light fiber into the end. You feed the light into the end of the fiber. That's the blue arrow. And as it travels along glass fiber, it always hits the side of the glass. And remember, it's relative to the normal. It's hitting the glass relative to the normal at an angle theta 1 greater than the critical angle. It might be from glass to water or glass to air. It's greater than the critical angle. Therefore, no light escapes the fiber. It's all completely, totally reflected. So even though this glass fiber may be bent, the light can travel for long distances. By long distances, I mean cables that go across the country, that may go underneath oceans, etc. Very important technique, because if you want to put a cable underwater, if you want to put a copper cable, it may corrode, it may make electrical contact with the salt water, etc. And copper is expensive. Glass fiber is cheaper than copper. Glass fiber is not going to corrode in water. You don't have a problem with electrical contact. So these kind of fibers that are used for transmitting data, they're also used for a technique called endoscopy in medicine to look inside the body. Other applications as well. Very, very important, significant phenomenon based on the fact that theta 1 is greater than the critical angle, theta C. Therefore, it travels along that fiber for, great distances, meaning hundreds or thousands of kilometers, thousands of miles, without escaping the glass fiber. I thank you once again for listening all the way to the end of the video.